Uh, before I start, I'm just showing three windows. Participants, can you please tell me if you can see all? This is the slide, this is the board or the copy, this is the SPSS. Are
Yes,
all the
we
three
can see
visible?
it, sir.
Yes, sir.
Okay.
Visible.
So our topic today is testing of hypothesis. Now, before we go to hypothesis, let us just let me just tell you a few things. Our discussion today, in our discussion today, we will try to use as less as possible statistical jargons and keep the language simple. Say when we are using Excel, in the Excel sheet, I just type 2 and 3 and I put the sigma sign, I get the total as 5. I only learn or we only know to use that when we need to add, we will have to use the sigma sign. We are not interested in what programming Excel is doing. Same way, in social science, statistics is part of our research. Here, we will limit our discussion only to that extent how far statistics will help us to do our research, under what situation, which test to apply, and through SPSS, how to interpret the result. As much as possible, we would like to avoid uh, statistical jargons and keep the discussion as simple as possible. I will be, for testing of hypothesis, I'll be taking up examples and we will be seeing through SPSS how to do them and from the SPSS how to interpret the results. For doing this, few points or few idea we should have, we will only discuss those and we will move to hands-on. So testing of hypothesis, before we do testing, what basically is hypothesis? Well, it is defined as hypothesis is an assumption about the population parameter. In simple terms, basically, hypothesis is any idea that can be tested based on any evidence. So any idea which we want to test based on some evidence, that is a hypothesis. Say for example, we say cigarette smoking will lead to lung cancer. Now, this is a hypothesis. Whether smoking will lead to lung cancer or not, that needs to be tested. Or say, in this class, the average weight of this class is 58 kg. This is my hypothesis. Now, whether actually this is 58 or not, whether this hypothesis is correct or not, that needs to be tested. So basically, hypothesis is any concept or any statement that needs to be tested so that we can say that this concept or the statement or the idea which we are having, that is credible. So this hypothesis, this serves as a starting point for further investigation through scientific method. Another term which we are coming across here is population parameter. What is this population parameter? In statistics, population parameter is a number that describes something about the group or the population. Say average weight of this class is 58 kg. So this 58 kg is the population parameter. What it is describing? It is describing the average weight of this group or this class or this population. So parameter, it is the characteristics of your population like mean or your variance. In my example, the average weight of the class is the mean. So before we go into any sort of analysis, the parameter must be analyzed. The parameter must be identified. Now, once you have developed your hypothesis, or once we have developed this idea that we need to test, we will go with the testing. So once the hypothesis is done, we will go with the testing. Say I have said the average weight of this class is 58 kg. So of this class means this class is the population, average weight is the mean. So the population mean is 58 kg. Whether my assumption, whether it holds good or not, whether it is credible or not, that needs to be tested. That is testing of hypothesis. How to go ahead with the testing? So from this population, we will collect some sample data. In this case, say we will calculate, so we will take some data from the class and we will calculate the mean weight. And using that, we will decide whether the hypothesized value for us, the hypothesized value is 58 kg, whether it is correct or not. So this is how your thing will look. There will be a population. From that population through sample, here we have taken as random sample. Through population, from this we take a sample. That sample statistics, we calculate the mean of the statistics, and we check whether from that through testing whether the population mean 58 kg, whether it is correct or not. So here the sample will represent your whole population. In every class there is a CR. What does that CR do? That CR represents that class. So that class is the population and that CR is the sample from that population. So that sample will represent the population. So from that population, we will draw a sample, we will test on the sample, and we will try to comment on the population. We will try to see whether the hypothesis that we have developed, whether it holds good or not. That is what is to be done through testing of hypothesis. Now, say when we are to test the hypothesis, we have said we will collect the sample data from the population. Next, we will use that sample and determine whether the hypothesized value and the actual value of the sample which we have taken, whether there is any difference or not. In the example which I am using to explain this, I am taking the hypothesized value is 58 kg. Now say of this class, I have taken a sample of say 15 students. Now of that 15 students, I have calculated the sample mean weight of those 15 students. Now actually this 15 students weight will not be equal to 58 kg. There will be a difference. 58 is my hypothesized value, that is the hypothesis I have taken, and the actual computation of that sample will be different from that 58 kg. We need to judge whether this difference is significant or not. The smaller the difference, the larger is the chance that the value, hypothesized value for that mean is correct. And the larger the difference, that is the chances of the difference will be more. So if the difference between that hypothesized value and the mean is small, then there is greater chance that our hypothesized value for the mean is correct and vice versa. This is the testing that we will be doing here. So how to carry on with the test? In hypothesis testing, first we will assume something, or we will develop a hypothesis for which we will give a numerical value. Numerical value, it can be, say in my case, I have given it 58 kg. Now, my assumption is the average weight of this class is 58 kg. So this assumption, which we will test, this is known as null hypothesis, represented by H0. So your null hypothesis is H0, which will be written as H0 is what? It is mu. Mu is the population mean, which is equal to 58. The average weight of the class of the students is 58. This is my assumption. This is my null hypothesis, which I will test. Now, we will begin with that assumption that this null hypothesis is correct, and we will carry on the test and decide whether my assumption is right or wrong. against any null hypothesis, there is an alternative hypothesis. The null hypothesis is the mean weight of the class is 58. So the alternative hypothesis will be the mean weight of the class is not equal to 58, which is represented by the alternative hypothesis is represented by H1. So it will look like this. H1 will be mu not equal to 58. It may be more than 58. It may be less than 58. So the assumption or with which we start, that is the null hypothesis. And against that null hypothesis, we will have some alternative hypothesis. Once the hypothesis is developed, we will proceed with the testing. The first step is to set up the hypothesis, which say we have done here. The null hypothesis is 80, mu is equal to 58, and the alternative hypothesis mu not equal to 58. Next, we have to set up a suitable significance level. What is a significance level? Say, in statistics, generally, we take significance level 5% or 1%. 5% level of significance, the level of significance is denoted by alpha. 5% level of significance means out of 100, there is 5 per chances that we reject the null hypothesis. If we are testing it, the level of significance is 1%, then out of 100, there is 1 chance that we will reject the null hypothesis. In other words, we can put it that there is 95% chance that the null hypothesis will be accepted. So 95% chance that the null hypothesis will be accepted. So this is the setting up of the suitable significance level. Once we develop the null hypothesis, we will select a significance level and we will test at that significance level whether the null hypothesis holds good or whether we need to reject it. Now, what should be that significance level? That significance level can be anything, but generally 5% or 1% level of significance is used. Significance level is denoted by alpha. So, hypothesis developed, the significance level is set up. Now, once the significance level is set up, then we will determine the test statistics. The test statistics, depending on the size and nature of data, we will develop the test statistics, which we will see later on. It might be a t-test, it might be a z-test, it might be an f-test, it might be a chi-square test. Whatever it is, whatever the test we are doing, we will develop the suitable test statistics. Now, once the suitable test statistics is developed, we will determine the critical value from the table. Now, if the distribution, it's a normal distribution, say if we are testing it at 5% range, if at 5% level of significance, this side it is 2.5%, this side it is 2.5%. If the value which we have taken, if it is false, if the test statistics which we develop, if it falls in this white area, that means we will accept the null hypothesis. And if it falls in the shaded area, then we will reject the null hypothesis. Now, how that is to be done? Once we develop this test statistics, we will, from the table, we need to calculate the critical value. We will compare the tabulated value with the critical value. If the tabulated value is more than the critical value, then we will accept, we will reject the null hypothesis, or else we will accept it. Now, this is just a discussion which I have just one step after another I am telling. Later on, when we will be taking up the example, we will see this. At a glance, this is how the hypothesis testing will look like. We will have to formulate the null hypothesis and the alternative hypothesis. Then, depending on the data and the size and the type of the sample, we will select the appropriate test, we will select the level of significance, and then we will calculate the test statistics. The method which I have discussed just now, that is the classical method of comparing the test statistic value with the tabulated value and deciding on the outcome. Alternatively, from the software result, from the probability, we can compare the alpha and we can come to that same conclusion whether to accept or to reject the null hypothesis. In reality or in practice, we will use this. We will we will use the probability and compare it with alpha, and based on that, we will decide whether to accept or to reject the null hypothesis, and we will draw the conclusion. One example I will take, the very first one. We will see both the method of checking through classical method as well as comparing of the probability with the alpha, and we will decide whether to reject the null hypothesis or not. Thereafter, for all other examples, we will straight away compare the probability with the alpha to draw the conclusion. This is the basic of hypothesis testing. If anybody, if you want to add something to it or any other discussion is required, please.
No, sir.
Okay. Sir, why we are always taking the null hypothesis for testing, not alternate hypothesis?
Whenever we develop an idea, that this is to be tested, that is known as null hypothesis. Anything against that is alternative. So whenever you want to test something, that is by definition that is called the null hypothesis, that is taken to be true. Anything against that definition is the alternative hypothesis.
Okay.
Just now, when we were talking about the classical method, whether the value, the tabulated value, falls in this critical region or not. If it falls in the critical region, we are telling it that the null hypothesis will be rejected. Now, it can fall on this side, it can fall on this side also. So, if okay, if we reject the value of a sample falling on either side of that tail, then it is known as a two-tailed test. Say if their value falls on either this side of the region, shaded region, or this side of the shaded region, it is a two-tailed test. And if it falls on any one side of the tail, then it is known as a one-tailed test. Say you are testing that the mean is 10. This is your null hypothesis. Your alternative hypothesis, the mean may be greater than 10. You're taking the mean weight as 10. That is your null hypothesis. So your weight can be greater than 10. It can be less than 10 also. So if you are just telling that no, my mean weight is up to 10, alternative is more than 10, that means it will fall on one side. Or your alternative is your mean weight is less than 10, that will be on the left side of the tail. But if it may be more than 10, it may be less than 10, either or, then it will be a two-tailed test. Say if the mean weight is 10, the alternative hypothesis is the mean may be greater than 10, the mean also may be less than 10. So it may be on this right side greater, it may be on the smaller side less. So both the side of the critical region it will fall. So that type of test is known as two-tailed test. And if you're just testing one aspect, that the mean weight should not be more than 10. So your alternative hypothesis is mean weight is greater than 10. So it is on the right hand side. Or say your null hypothesis is your mean weight should not be less than 10. So alternative hypothesis is mean weight is less than 10. Less means it will fall on the left hand side. So if you are testing either less than or either greater than, then it is a one-tailed test. Depending if it is on this side, this is a right-tailed one-tailed test. If it is on this side, this is the left one-tailed test. And if you are testing something whose alternative can fall on either side, maybe greater, maybe lesser, then it is a two-tailed test. It will fall either in this shaded region or in this shaded region. So the test which we will be doing, that may be one-tailed test or that may be two-tailed test. Now, when we are dealing with the testing of hypothesis, there can be a situation, say, you have developed a null hypothesis which is true, which is actually true, and your test result says so. Very good. You are testing a null hypothesis which is actually false, and your test result rejects your null hypothesis. That is also correct. But you think of a case where the hypothesis which you have taken, actually it is true, but the test result rejects it. The statistical result rejects your hypothesis. Or say, the hypothesis which you have taken, that is actually false, but your test result accepts it. So this third and fourth case, there is a problem. The third case, when the hypothesis which you have taken is actually true, but the test result rejects it, that is known as type 1 error. And in the fourth case, where the hypothesis which you have taken, that is actually false. Actually false means my hypothesis is average weight of this class is 58 kg, but actually it is not so. Actually it is it is not 58, but the test results statistically shows us no, it is correct. That is the hypothesized figure 58 kg, it is correct. Then that type of error is known as type 2 error. There is a classical example which almost all textbook take, that is a courtroom trial example. Say when a trial is done, the defendant, the hypothesis is, the basic assumption is, until and unless one is proven guilty, he will be taken as innocent. So the null hypothesis is the defendant is innocent. Now, actually, whether the defendant is innocent or not, that's a different case altogether. But it is assumed, the null hypothesis is that the defendant is innocent. Now, actually, in real life, the defendant is the convict is innocent, and our test result says so. That is acceptable. The next situation is he is actually not innocent. Our null hypothesis says he is innocent, but actually he is not innocent. But the test result rejects our null hypothesis. That is also correct. He is not innocent. The test result says that the null hypothesis that he is innocent is rejected. But take a case. The null hypothesis is the defendant is innocent. Actually also he is innocent. But the test result rejects the null hypothesis that he is innocent and accepts the alternative hypothesis that he is not innocent. That type of error is known as type 1 error. And the other cases, the defendant is not innocent, but the test result accepts the null hypothesis that he is innocent. That type of error is known as the type 2 error. So first case, your null hypothesis is correct, it is accepted, right decision. Next case, your null hypothesis is rejected, and that is also a correct decision. He is guilty. The null hypothesis that he is not guilty is rejected. But type 1 error, that is the hypothesis is true, but actually it is true, but the test result rejects it. Actually he is innocent, but the test result, the H0 is rejected. So a wrong decision comes up. It is as per the result, he is guilty. So that is a type 1 error. And the type 2 error is actually he is guilty, but the test result shows that the null hypothesis is accepted and he is taken as not guilty. So these type of error, type 1 error and type 2 error, needs to be taken care of or to be kept while doing the hypothesis testing. Now, dealing with null hypothesis, dealing with type 1 error, type 2 error is altogether a separate discussion. For the time being, just for the theoretical discussion, let's keep these two in mind, that if the rejection level, that is the alpha, if you're using, if you're taking it as a very lenient, say if I am testing it at say 10%, 15%, 20%, the chance of type 1 error coming in becomes more. And the chance of type 2 error coming more is, it will be if you're using too small a data set. So your type 2 error will come. So there are other tests also that needs to be taken care of. So with this concept about hypothesis testing, let us move to the testing part. Anything, any discussion? Now, the hypothesis testing basically are two types. Parametric test and non-parametric test. The parametric test generally assumes that the distribution of the sample is normal, that is the normality condition. But the non-parametric test, it is distribution free. The data, we do not assume that the data is drawn from any particular type of distribution. So this is the basic difference. It can be dealt in details, but the basic difference between the parametric and non-parametric test is that for parametric test, it's basically the normality condition it is assumed, and for non-parametric, it can be any type of distribution. So for parametric test statistics, which we will cover here today, is t-test, z-test, ANOVA, paired t-test, and time permitting, we will take up the chi-square test from the non-parametric. Though our discussion mainly here will be limited to the test for normality. Now, out of the test that is applied, that is, we will talk about t-test, z-test, paired t-test, and ANOVA. First, we will see when to apply which test that we are to decide. Once that is decided, then we will see how the test is done, and then we will interpret the results. Now, when we will apply t-test. Now, t-test, basically that distribution, the t distribution is almost similar to a standard normal distribution. The main thing here, it is for t-test we will use when the sample size is small. As a thumb rule, any sample size less than 30 is a small sample. So we will use the t-test when the sample size is small and this population standard deviation is not known. We don't know what is the population standard deviation. Then we will apply the t-test. Now, in t-test, when we will calculate the table value, earlier we have talked about table value, comparing the test statistics with the table value. There is a thing called degree of freedom. Now, the software will take care of the degree of freedom. You need not calculate it. Degree of freedom basically means the number of pieces of information that is going in for that calculation. So that is the degree of freedom. Now, since one example we will check, that is we will take up through we will use the table value to decide whether to accept the null hypothesis or not. For that purpose, I am just telling the degree of freedom basically is n minus 1, number of observations minus 1. So if you are using two group, then it will be both the group observations n to be added minus 2. So that will be when t distribution will be there. Now, if the sample size is more than 30, then we will move to Z test. And if we are having more than 3 samples, then we will use ANOVA. So first, we will be taking up the t-test. T-test basically are of 3 types of test. One sample t-test, two sample t-test, and paired t-test. Now, what is this one sample t-test? When to use that? Now, one sample test is when you test to compare the mean of a sample with the predetermined value. In my example, which I had taken earlier, the mean weight of that class is 58 kg. That is my hypothesis. Now I will test it whether the mean weight of that population is actually 58 kg or not. Whether the hypothesis which I have taken, whether it is correct or not. So if it is correct, if the null hypothesis is accepted, then it is correct, or else the null hypothesis will be rejected. So when this is a one sample test to compare mean, two sample test may be of unpaired group, may be of paired group. Unpaired group or independent group means the data is collected from two separate groups. Say, when to use, for example, say this, in this example, a man is placing order from pizza for two different companies. The time taken from company A, that is one sample. The time taken from company B to deliver the pizza, that is another sample. Now, he wants to know whether there is any significant difference in delivery time of either of that company. In that case, a two sample test, or also known as independent sample two test, will be used. Here, both the sample which we are using, they are independent. They are unpaired. So one sample comes from the pizza company A, their delivery time. Another sample comes from pizza company B, their delivery time. Whether there is significant difference in their delivery time, whether there is any significant difference in their delivery time or not, that one wants to know, that is to be tested. So that is two sample test. It is used to test whether the unknown population mean of two groups are equal or not. And the third type of test is the paired test. Paired test means, say, I have taken sample from two groups where I can pair. Say, day one, the rainfall in one area, rainfall in another area. Day two, rainfall in one area, in that area, rainfall in that. Say two area A and B. Day one, their rainfall. Day two, their rainfall. Day three, their rainfall. These I can pair. First day, what is the pairing? Day one A and B. Day two A and B. So if I want to test, is there any significant difference? Then that will be a paired t-test. Or say we have done some experiment and we want to check the effect, whether before conducting that what was the position, and after conducting that experiment has the position changed. That is, we can pair before after. So if we get a sample two samples which we can pair either before, after, or we can relate to some common base, then we can use the paired t-test. It is also called dependent t-test. It is a statistical procedure which used to determine whether the mean difference between two sets of observation is zero. So we will pair and see whether their mean observation or whether there is any significant difference between them, that we will test. Or it can be test to measure results in pair of observation. That is the second thing which I am talking. Say a person is, there are a group of 10 students. Before taking coaching, they have got some marks. After taking coaching, their marks has changed. So for a student before coaching, after coaching, when their marks, is there any significant difference in their marks? Whether coaching has played an important role in their performance, that can be tested through the paired t-test. So basically, these are the type, or these are the three types of t-test: one sample test, two sample test, and paired t-test. Up to this, anything?
No, sir.
Let's take up the first one sample test. See here, I have 12, a sample of 12 men. This is the, from the average systolic blood pressure of a normal male is supposed to be about 129. Measurement of the systolic blood pressure on a sample of 12 adult males from a community whose dietary habits are suspected of causing high blood pressure are listed. So from a group, 12 male blood pressure has been taken. It is the blood pressure is supposed to stay 129. Up to 129 is the average blood pressure. Now, that group has the chance of high blood pressure. The food habit is such that there is chance of high blood pressure. So a group of 12 sample has been collected, 12 by blood pressure has been collected. Now we need to test at 1% level whether that community is having, or whether that group is having high blood pressure or not. That we will test. Before testing that, one more thing also can be done, also can be tested here, is to find the range of the blood pressure of that adult of that group. How to do? Now, I have this data already with me in my SPSS file. Is the SPSS visible?
Yes, sir.
Yes, sir.
Okay. This is the blood pressure of the sample of 12 male adults collected. First, we will see that whether this blood pressure, what is the range of the blood pressure of this group. So we will go to analyze option, compare mean, one sample t-test. The only sample we are having blood pressure, you select this as the test variable. We are to test it at 95% confidence interval. So the alpha value should be 5%. So 95% confidence level, go to option. By default, it is 95. If you want to test it at 99, you can change it to 99. So here in this case, it is asked 95. Okay. In this one sample test, there is a 95 confidence interval of difference, lower and upper. So the lower blood pressure will range on an average from the lower blood pressure will range from 124 to as high as 142. So this is how we will calculate the range of the blood pressure. So though this is not a part of our topic basically is to test the hypothesis. Now, why do we test? This is a small sample test of 12 people, and we are basically what we are testing. We are testing the mean. The mean we are taking it as 129. So, what will be the null hypothesis? Say the null hypothesis here is H0 mu is equal to 129. Actually, we are testing for higher blood pressure. So it can be even written as this way. That is, the blood pressure should not exceed, the maximum blood pressure acceptable is 129. Okay, let's write it this way. The null hypothesis is 129. And against that, we are testing that for high blood pressure, alternative, there is 129 is the normal acceptable level. So this is the null hypothesis. Against that, the alternative hypothesis will be mu greater than 129. So this is how we will write the hypothesis. Next, it is to be tested at 1%. So our alpha is 0.01. So this is the hypothesis is developed. Let us run the test. So this is t-test, one sample t-test. So go to analyze. Let us choose compare mean, one sample test. Analyze, compare mean, one sample test. Now, since we had already done this, blood pressure is selected. You can reset it. So our test variable is blood pressure. Now, mu is 129. That is the null hypothesis. When we were talking about calculating the interval, our test value was 129. Now, here we are one sample test of mean. The mean is 129. Put 129 under the test value. Go to option. By default, it is 95% confidence interval. So our critical region, our level of significance is 1%. Alpha is 0.01. So 1% means the confidence interval will be 99%. So you change it with 99% confidence, we can say that the null hypothesis will not be rejected. Alternatively, it can be said that with 1% chance that the null hypothesis will be rejected. So our alpha is 1%. So you change the confidence level to 99, and then once done, apply OK. This is your test result. Now we will check both this one classical through the classical way. Only one example only we will check through the classical way and also through the p-value. Now here, how many observations are there? We have taken 12 observations. So our degree of freedom will be 11, n minus 1. You see here it is calculated as 11. So our degree of freedom is n minus 1, that is 11. And what is our t value? The t value here is, we have computed, is 0.994. 0.994. This is the t value. So we need to check t t-value at 1% level or degree of freedom 11, that value we need to calculate it from the table. This is a t distribution table. It is a one-tailed test and we are testing it at 1% level. So we will check one-tailed 1%, 0.01. Our degree of freedom is 11. This is 11. So you go down one tail 1%, that is this column, degree of freedom 11. It is coming to 2.718, that is 2.72 approximately. So 2.72 is the table value or known as the critical value. So this is 2.72. So this is the test statistics and this is the critical value. If the value of t is more than the critical value or the table value, we will reject the null hypothesis. Now the question is, can we reject the null hypothesis here? Our t value is 0.994,
No, we can accept here the like.
which is less than the critical value. The critical value computed is 2.72. So we fail to reject the null hypothesis. Since we fail to reject the null hypothesis, that means we can conclude that there is not enough, or we can conclude that there is not enough evidence to say that the group or this community male is having high blood pressure. So this is the testing. This is the classical way of testing. But classical way of testing requires looking at the table, comparing, and so on. Henceforth, we won't be using this way. We will go with the other method. Which is the other method? Other method is you compare the probability with the alpha. If the probability value is less than alpha, we reject null hypothesis or else we will accept. See here, the probability value, it is given here. This 0.342. This is the significance. This is the probability value given for a two-tailed test. So for a one-tailed test, the software, it is giving it in two-tailed. So we have to calculate it for a one-tailed test. So calculating it for a one-tailed test means basically just half of that. So p-value will be half of the significance of two-tailed test. So this value is 0.342. So half of that is 171. Now this is the p-value. If it is less than 0.01, we will reject the null hypothesis. Now, but this value is more than 0.01. So the null hypothesis cannot be rejected. So basically what we have to do, we have to compare, we have to get this value. Now, for whatever the level of significance, here it is 1%. Suppose the level of significance, we will compare this with 0.01. If this is less than 0.01, we will reject the null hypothesis. If it is more than 0.01, we will accept the null hypothesis. Now, suppose we were testing this at 5% level. So this 0.171, we will compare it with 0.05. If 0.171 also, it is more than 0.05. So we cannot reject the null hypothesis. So whichever way you go, whether through the classical method or through the p-value method, it will give you the same result. But We will classical method, lots of hazard. We need to check the table, etc., etc. We won't take such pen. Henceforth, we will just compare the significance value with the alpha. If the probability value is less than the p value is less than the alpha, we will reject the null hypothesis. So this is for a one sample test. Anything, if any steps not clear?
No, sir. Clear.
Let's move to the second test. Second is two sample test. Two sample test, unpaired group. There is no relation. We cannot pair the observation. Say the pollution index of air sample of two city, of two area in a city, it is taken. This is area A and this is area B. We need to check whether there is the average pollution index, whether there is a significant difference. That means whether the pollution level in both the area of a city there is a significant difference or not, that we will check. So altogether 1, 2, 3, 4, 5, 6, 7, 8, 8 observations. Small sample, but there are two sample is taken. As against the earlier example, that was a single sample. So here we have taken two samples. So here we are having two samples. So we will, but they are not paired. This one is not, say for day one, if area A was 2.92 and area B was 1.84. For day two, if area A was 4.69 and area B was 3.44, in that case, we would have said it is paired. But in this case, it is not paired. This is just the 8 observations of two area. Now we need to check whether there is significant difference in the average pollution level of these two area of a city. Let me go to SPSS. This is the data. It's already I've kept it in the SPSS. Now, this is the population index for area A, and this is the population index for area B. Now, if I click here, if I toggle in this value level, if I just press here, you will see all area A is marked 1, all area B is marked 2. SPSS cannot understand area A, area B, area C, or town XYZ. It will understand 1, 2, 3. So when we are entering this data in SPSS in the variable view, this is the one is the index, that is the actual reading of the pollution, and next is the area. So when we have taken that area under value, when you will take the value, see already area A and B is given. How to put it? So there is a third area, that is C. Then the value will be 3. Under level it will be area C. Add OK. Now say if I enter this as 3, let me put a toggle here, it will be area C. I put 1, area A, I put 2, area B, I put 3, area C, and so on. So you need to make SPSS understand. So for that 1, 2, 3, it is given as a label here. So these are extra. Just for the sake of the discussion, I have just now entered. Let me clear this 4. And in the variable view also, though it won't make any harm, still I remove this. So the areas are denoted by 1 and 2. So this is the pollution index I'm having. So how to test for hypothesis? You go to analyze. Same, compare mean. Instead of one sample test, this is a 2 sample test which are not paired, which are independent. So select independent sample test. We are basically doing this one. Two unpaired group. So analyze, compare mean, independent sample test. Now, which is the test variable? Our pollution index is the test variable, which written as indexed. You select it and transfer it to test variable. And you are grouping it, the test variable, by area. Transfer that area as a grouping variable. See, it's giving 2 question mark. You need to define this. So define group. The first group A, we have called it SPF given 1. And the second group we have, that is B, for SPSS we have taken as 2. 1, 2, continue. Level of significance in our problem was 5%. So you can click the option. By default 95% confidence is taken, so we are testing it at 5%. We need not change anything. So we will apply we will now run and we will get the results. Now before that, let us just write the hypothesis. So here it is the mean of 2 area. So the null hypothesis is that the mean pollution level of area A and area B, there is same. There is no difference. An alternative hypothesis is mu A not equal to mu B. Some people, instead of this, write it this way, 80, such that mu A minus mu B is 0. Basically same thing. There is no difference. No difference means both are equal. Some people, instead of this, write it as UA minus UB is equal to 0. In that case, the alternative hypothesis will be mu A minus mu B not equal to 0. And we are going to test it at 5% level of significance. So everything selected. Let's run it. Okay. Once we run it, we get the output here. This is the T statistics. Now you see, 2 things are given. Equal variance assumed, equal variance not assumed. Now we are checking the pollution level of 2 different areas of a city. Now the 2 different area, if they are exactly same, then we will assume equal variance. But 2 area may not be same. Say the for the pollution level, say the industrialization in one area may be more than the other. The plantation in one area may be more than the other. The vehicles running in one area is maybe more or less than the other. All these things contribute to the population is pollution. So both the areas are not actually same in total. So we are assuming, this is an assumption, we are assuming equal variance, not, we are assuming this one, equal variance not assumed. So here, this is a two-tailed test. Two-tailed why? Because we are assuming mean of both the pollution of both the areas same. Alternative is not same. It may be more, it may be less. So either or. So this is two-tailed test. So we need not calculate anything. The p-value it is given here is 0.162. And what is the criteria, testing criteria? Alpha is 0.05. So p-value here
I
is,
will stay.
yes, anything? So p-value here is
0.0881.
0.162. This one, madam.
We have to divide it by 2.
No, in the earlier case, it was a one-tailed test. Why one-tailed test? The
Yeah, yeah.
blood pressure should more. We are only checking the more aspect. So device that was two-tailed, we converted to one-tailed. But here it is the mean is same. It may be same, it may not be same. It may be more, it may not be more. So it is a two-tailed. So earlier, since it was one-tailed, so we divided by 2. But here it is two-tailed only. We need not divide anything. This is given. So 0.162. So the p-value is 0.162. And our alpha, it is we are testing it at 5% level. So the p-value is more than the alpha. So we fail to reject the null hypothesis. If the p-value was less than 0.05, we would have rejected the null hypothesis. So since we fail to reject the null hypothesis, we can comment that there is no significant difference in the average pollution level of both the area of the city. Am I communicating? Is this clear?
Yes, sir.
Okay. So So this is the second one, two sample test of unpaired group. Now we will take the third one, paired test of two group. The pairing may be either, it can be before, after of a particular event, that pairing can be done, or it can be for a particular case. For one day, this is the observation, for another day, this is the observation. So this same problem, the same example which we had taken just now, this is the area of A, the pollution of area A and area B. This can be translated into a paired t-test with some additional information. Say, it is given for day 1, this is the pollution of area A and area B. For day 2, this is the pollution of area A and uh, area B. So now it is becoming a paired data. Say, why paired data? Why paired sample? First day, this is the pollution of A and B. Second day, A and B. So now if we are to check whether there is a significant difference in the average pollution level of both this area, we need to use the paired t-test. It is a small sample and it is paired. So that same example, we will use it for SPSS. Here, no need to identify it as 1 and 2 because area A, this is the observation, area B, this is the observation, day 1, day 2, and so on. These are the observations. Let me clear off the earlier thing. So what will be the null hypothesis here? The null hypothesis here will be there is no difference. What is this say? This is area A population, this is area B population. So if there the difference between A minus B, that will be the difference. Say, is that difference significant or not? That we need to test. So a null hypothesis will be the mean difference not equal to 0, and alternative hypothesis is mu d not equal to 0. We are going to test it at 5% level. So this is the hypothesis. Let's go to analysis. Compare mean. Now this is a paired sample. We will be applying paired t-test here. So choose this option as paired t-test, paired sample t-test. A and B, select both A and B together and transfer it here. So this is the paired variable A and B. Option by default 95% selected. So we are testing at 5% level of significance. Okay. Let's run the test. These are the test results. So this is a two-tailed test. The difference may be more, difference may be less. We are telling that the difference, there is no difference. So the significance level is 0.000. So this is the probability is 0.00. So our p-value is 0.00 and our alpha is 0.05. So since the p is less than their alpha, we reject the null hypothesis that there is no difference between the mean pollution level of this paired sample, and we accept the alternative hypothesis that there is a difference in the mean pollution index for both these two areas. So this is how the different t-tests are used. One, for the first one is one sample, the second one is two sample unpaired, and the third one is two sample paired. So all are small sample tests. Now, for this paired one, we will use another example. We will check this with another example. See, these are the marks given for 20 students. They have 20 students, these were the marks. Now they have taken a coaching or they have taken one module. After that, their marks have, this is the marks after that taking up of the module. Now, the question is there a significant difference in the performance, average performance of the students while after taking up the coaching or not. Even in the last example, I haven't done it that way. Say, we were testing the difference. You can create another variable, which is the difference variable. How to create? You go to transform, compute variable. Give any name to it. Say, I call it D or diff, whatever it is. Now, what is this difference? It is the difference between the post marks and the pre marks. So, post module, select difference minus pre module, select. This is the difference. Apply. OK. In the variable view, we have got another thing as another variable as difference. Let me apply the same test here. Analyze, compare mean, paired t-test. Now, which are the pairing? Pre and post module marks. Now, after coaching, we have take the marks should be, generally, if you take up the coaching, the marks will increase. In the difference also, it is taken as post minus pre. So post, you swap it, take it as variable 1, and the pre, that is, you take it as variable 2. Say at 5% level, that is to be tested. Okay. This is the test result. The test result shows your significance level 0.004, which is less than 0.05. So we reject the null hypothesis that there is no significant difference in marks and accept the alternative hypothesis that there is significant difference in marks because of the coaching. So the coaching has changed the average marks of the students. Is this clear?
Yes, sir.
Now, this same thing, this same example, same result, you can get it through other way also. Say here, we have used the paired t-test, pairing pre-module marks and the post-module marks. And we have developed or generated a difference variable. You go to your analysis, compare mean, one sample test, take difference as your sample. So you are testing the difference pre and post. Instead of that, the difference is generated. Take difference as the sample. At 95% level, test is okay. You see, we will get the same result. Significance, that is the p-value is 0.04 as of here. So since 0.04 is less than 0.05, we reject the null hypothesis and accept the alternative hypothesis. So the paired t-test data, those paired t-test situation can be converted. If you take the difference, you can use the one sample t-test also to get the same result. Instead of pairing, you get the difference and you can apply the one sample t-test. So it depends on the person who is using which test he will apply. So this is all we have from t-test. So one sample t-test, unpaired two sample test, and paired two sample test. So any further discussion on t-test or anything you want to add to this? Next, from t-test, we move to z-test. Now, z-test follows a normal distribution, and we will use z-test for a large sample. That means the sample size is more than 30. Now, theoretically, it is said that the t-test can be used as a statistical test, which is used to compare and analyze whether the mean of two population is different from one another when standard deviation is not known. And in z-test, it is assumed that the standard deviation is known. So let us not go into all those things. We will apply the z-test in case of a large sample more than 30, which follows a normal distribution. So basically point number 3 and 4. One important condition for adopting t-test is that the population variation is unknown. And in case of z-test, the population variation is known. Now, one problem with z-test is that in SPSS, you directly cannot you cannot compute your Z, you cannot test through your Z test. So either you need to write a code, or there is another method of using that SPSS indirectly to calculate the Z test. We will use that one. Let us take one example. A certain soft drink bottler claims that less than 20% of its customer drinks another brand of soft drink on a regular basis. So his claim is that less than 20% of the customer will drink another brand. So a random sample of 100 customers, a sample of 100 was taken, and the result shows that 80 in fact did drink another brand. So his claim was that at less than 20% of the customer drink another brand, and from that sample of 100, the result shows that 18 of them were drinking another brand. Now, the question is, does this sample support the bottler's claim? Whatever claim he has made, is it supported? You have to use 5% level of significance. Now, this is a one proportion test of a large sample more than 30. So we will be using the Z test. So what will be the null hypothesis here? Null hypothesis is 80 is proportion should be 20% and H1 proportion less than 20. It's the bottler's claim that less than 20% of the people use drink other brand. So we can write it 0.2 H1 so this is the null hypothesis and alternative hypothesis. The level of significance is 5%. Now, in SPSS, we don't have any direct command for carrying out the Z test. So we will do it in a roundabout fashion. Here also 18 out of the sample of 100, 18 take the same brand and 18 drink other brand. So the bottler's claim is less than 20% of the drink other brand. Now we have to test whether this claim is correct or not. So here also, when you are taking the value of the brand one, those drinking other brand is termed as one, and those drinking the same brand is termed as two. So 8 of the sample of 18, sample of 100, 18 drinks other brand and 82 of them drink same brand. So for carrying out the Z test, first you need to weight the data. Data, weight cases, select weight cases by, transfer your count. Press OK. Again, go to analyze. Now, here you see all the options are of t-test and ANOVA. So no z-test is given. So we will go to parametric test, non-parametric test. From the dialog, legacy dialogues, we will select chi-square. Once we select the chi-square, take the brand as the test variable list and the value we are testing that 20% of them is not drinking this brand. So first value is 0.2 and 80% is drinking this brand. Second value is 0.8 and once it is done, then press OK. Now option, we are testing it, now press OK. Once you press OK, the results comes, but there is no question of any, the output doesn't give any Z score. Instead, it gives the chi-square as 0.25. So the relation is Z is root over chi-square. So what we will do, the chi-square value is 0.25. Square root of that will come to 0.5. So this is the Z score. Indirectly, we are computing it from the chi-square. Now, what will be the sign of Z, positive or negative? Now, check the residual. Whatever sign that residual will give, that will be the value of Z. So in this case, the value of Z will be minus 0.5. So what basically we are doing, we had run the chi-square test. Once we have run the chi-square test, the relationship between Z and chi-square is Z is square root of chi-square. We have used that square root and got the value of Z. Now, the sign, whether the Z will be positive or negative, will depend on the sign of the residual. So sign of the residual here is minus. So it is minus 0.5. Now, for Z test, if we check the value of P, what is the value of P? P value, it is 0.617. That is for two-tailed. Now, this is a left-tailed test, left one-tailed test. So, the P value 0.617 divided by 2. So, P value will be 0.617 divided by 2. It is 0.3085 0.3085 is the value of P, and we are testing it at 0.05. So since the P value is more than the value of alpha, we fail to reject the null hypothesis. So we accept the claim of the bottler. Alternatively, since we are taking up only one, we are taking up Z for the first time. Like the T test, there are some table values of Z test. This is the Z test table value. So this is, we were doing it for at 5% level of significance. What was the level of significance? 5% level of significance, and the one-tailed test value is minus 1.645. One-tailed Z value is minus 1.645. So the computed value with the critical value, so critical value is minus 1.645. So the critical value is minus 1.645 and the computed value is minus 0.5. Now, since your Z value is not more than the table value, we fail to reject the null hypothesis. The basic thing is same. Whether you go into the classical way or you compare the P value, the thing is same. The computed value more than the table value, null hypothesis will be rejected. P value less than alpha, null hypothesis will be rejected. Whether T, whether Z, thing is same. So this is how we have used the table to calculate the critical value and to comment on whether to accept the null hypothesis or not. So in this case, we are accepting the null hypothesis that the bottler's claim is correct. So since directly we cannot apply Z test in SPSS, and since there is a relationship between Z test and chi-square test, so we have used the chi-square test, and from that we have derived the Z test value. Any questions or any other discussion, anything you want to add to it? It's open for all to add to this.
Sir, can you please repeat this last part, the critical value, why we took the negative value?
Okay. We are not directly getting any value. We are from the chi-square, we are deriving the Z value. How to derive? Chi-square square root will be your Z value, this one. The chi-square value, square root of that, it's the Z value. Whether the sign will be positive or negative, that will depend on the sign of the residual. So the sign of the residual is minus, so this will be minus. And you forget it's a left-tailed test. All right. So left-tailed sample, one sample test means it will fall in this negative region also. From there also you can say it is negative. But the thing is, you will calculate the Z value and then you will check the residual. The sign of the residual will be the sign of Z. Is this clear, madam?
Yes, sir. Yes, sir.
Okay. So this is a 1 proportion Z test. Next is 2 proportion Z test. How to deal with that? This is a 2 proportion Z test. Say a machine in a test of reliability of products produced by two machines. Machine A is producing 15 defective parts, while in the run of 280 parts it's produced, while B has produced 10 defective parts, while in the run of 200. Now, is there any significant difference in their performance? So, out of this 280, 15 is defective, and out of the 200, 10 is defective. Is there any significant difference in the performance of the machine? So proportionate defective of the total 15 of 280, and in case of the other machine it is 10 of 200. So the data is plotted here. So machine A, it is producing defective, and the good one, let us call it acceptable, and the machine B producing defective, and the good one, let us call it acceptable. While in the variable, in the machine 1, A is termed as 1, machine B is termed as 2, and in the quality also, defective is termed as 1, acceptable is termed as 2. In order to make SPSS understand the different machine and their quality. So machine A, defective items, acceptable items or good item. Machine B, that is 2, defective item, good item. So we are checking the proportion, we are taking the proportion of defective to total and commenting, and we will see whether there is significant difference in the performance. Now, out of 280, 15 is defective. So the rest 265 is acceptable. And out of 200, 10 is defective. So the rest 190 is acceptable. So the acceptable from the total, we have subtracted the defective and taken the acceptable range. So this is the data which is available to you. We will check whether there is any significant difference in their performance or in the reliability of the machine. So first, we will, just like in the previous one, we will take up the data, take wet cases, wet case by, this is the counting. Okay. Now, here also, we won't be able to calculate the Z-score directly, but it's a 2 sample, so we will use another alternative. We will go to analyze, descriptive statistics, cross tabs. There are two machines A and B, and the subdivision of that is the quality, defective and acceptable. So in the row, we will take up the machine. In the column, we will take up the quality. And we will click on this statistics. And in this statistics, we will check up the chi-square. Once we select the chi-square, continue, done, OK. This is the result which is available with us. Now, if you want, the square root of this chi-square will give you your Z score. But directly what we will do, we will check it from the p-value and the alpha level. So here p is 0.862 and our level of significance was 5%, so 0.05. So since 8.862 is more than 0.05, we fail to reject the null hypothesis. So at 5% level of significance, we don't have enough evidence to conclude that there is any difference in the reliability of the machine. So since Z test cannot be done directly from SPSS, in case of a single proportion and in case of two proportion, these are the two other way around we have used to calculate to get the result. Any question or anything you need to add to this? Here also, you can calculate the Z value by the square root of the chi-square, and then from the table you can compare the value and you will get the same result. But that way we are not going it. We are going with the simpler way. We are checking the p-value with the alpha. So since the p-value is more than the alpha, so the null hypothesis, we cannot reject the null hypothesis. So this is all what we have from t-test and z-test. Now, for one sample or two samples, depending on the size, we are applying t-test or z-test. Now, if there is more than two samples, three or more samples, in that case, we won't be able to apply this test. In that case, we will be applying the ANOVA. So where we need to check up the difference between two or more than two groups. So let's take one example and see how ANOVA is done, and we will conclude our session. It's already 4:40. So this is the classic example. You will find it everywhere. In a path, in a maze path, there are 3 colored doors. 5 mice were left on it. So the time taken to run the maze for each colored door, this is given. Now, the question is, does the color of the door has any effect on the time they take to run? So this path, every path, there is 3 different paths, one with red door, one with green door, one with black door. Now 5 mice are randomly selected, and and they were placed on this maze to run. So those five which were selected, they ran that red color in this, say, 9 minute, 11 minute, 10 minute, 9 minute, 15 minute. Another sample on the green colored maze through the green colored door, these are the time, and the black colored door, these are the time. Now the question is that does the color of the door have any significant effect on the time taken to run? So is there any significant difference between the average time taken to run? That is what we need to check. Now, here it is more than two sample, so we won't be able to use the t test or the z test, so we will be using the ANOVA. This is already, I have it already saved in the SPSS, the data. Same way, the different colors are mentioned as 1, 2, and 3. Red as 1, green as 2, and black as 3, in order to let SPSS know. Next, we will run the test. We will test for the hypothesis. What will be the null hypothesis here? That there is no significant difference on the runtime based on the color of the door. So 80, average runtime of the red door, average runtime of the green door, and the average runtime of the black door. There is no significant difference. And alternative hypothesis 8.1, at least one inequality. So at least one of them is having a difference. So this is the, just we are writing the null hypothesis and the alternative hypothesis. Let's carry on the test. Analyze, go to compare mean and select ANOVA. Once it is chosen, our dependent is the time and independent is the, the factor is the door color. Next, you select post hoc. Under post hoc, select Tukey. In the problem, the level of significance is 1%. So here, by default, it is 5%. You change it to 1%. Okay, and continue. Choose option and click homogeneity of variance. Once done, continue. Okay. We get the F statistics here. This is the result. We get the F statistics here, and the p-value is 0.000. Since the p-value is less than 0.01, we reject the null hypothesis that there is no significant difference between the three, red, green, and black. So at least there is one inequality. So we are rejecting the null hypothesis. Now, which is the inequality? The inequality here is the green is the inequality. You see here in the post hoc test, you will find here that green, their mean difference, both red and black, there it is significant. Moreover, from this homogeneous subset, you will see that black and red has been grouped under one head, while the green has been taken as a separate head. So our null hypothesis that all red, green, and black door will have no impact, that is not true. We have rejected that. And so testing of hypothesis is over there. The null hypothesis is rejected. Now, if for further investigation, if you want to find out that for which colored door there is a difference, this is the green colored door, there is a difference. So this is how we will deal when we are having more than two samples. So these are the parametric tests, which t-test, z-test, and ANOVA. So this is all we have for today's session. Thank you. And if you want to add anything or any other discussion, you're free. Please.